Last class we were discussing about kernels and ideals, and we saw that every kernel of a ring homomorphism is an ideal. An ideal is a subset of the ring such that it is an additive subgroup of the ring, and if A is an element of the ideal and R is any other element of the ring, then RA is also within the ideal. We saw two examples of homomorphisms and the kernel. The first homomorphism was from Z to Z mod 4Z, where phi of n is equal to the equivalence class containing n, that is n bar. So the kernel of phi was 4Z in the case where phi was from Z to Z mod 4Z. In general, if you have the same mapping, phi of k is equal to k bar from Z to Z mod 4, Z mod nz, then the kernel is simply nz, all multiples of it. Next example we saw was the substitution map from the set of polynomials with integer coefficients to the set of integers, where you choose for each element, for each integer, you have one substitution map. So if we saw the substitution map with integer 2, we call that phi 2 from z of x to z, and the image of any polynomial f of x that is in z of x will simply be f of 2. We saw that the kernel of that homomorphism was set of all polynomials such that f of 2 is 0, because 0 is the additive identity of the codomain. A set of all polynomials such that f of 2 is equal to 0 are simply the polynomials which have 2 as a root. And we also use some other fact. We use the fact that if you divide g of x by x minus alpha, the remainder is g of alpha. And then we said if we divide f of x by x minus 2, then the remainder is f of 2. So the kernel is the set of all polynomials such that f of 2 is equal to 0. That means that if you divide f of x by x minus 2, you get the remainder 0, which means that f of x is a multiple of x minus 2. So for an integer k, if phi k from z of x to z is the substitution map, so by substituting the integer k in place of x, then the kernel of phi k will be all polynomial multiples of x minus k. That is all polynomials of the form x minus k into h of x, where h of x is either an integer or constant polynomial or some polynomial in z of x. We saw up to this much in last class. No issues with any of this content, right? Okay. For reference, I'll write it so that if you want to, you can refer it later. Okay, now we have the following lemma. We saw that um, we saw one homomorphism from Z to Z mod nz that was given by phi of k is equal to k bar. So each integer is mapped to the equivalence class containing that integer under modulo n. So there the kernel was the set of all multiples of n. Those are the integers that go to 0 under modulo n operation. So nz was, and we know that every kernel of a homomorphism is an ideal. So each set of the form nz is an ideal of the set of integers. We saw that. Now we show that, those are the only ideals of z. So any ideal of z has the form nz for some non-negative integer n greater than or equal to 0. Can you prove this? Well, nz is not homomorphic isomorphic to zn. Z mod nz is isomorphic to zn. Nz is all the multiples of n. Yes. Actually, this you can prove from the beginning, but we already proven kind of proven this because we proved that subgroups of nz, additive subgroups of z are all of the form nz. Since any ideal has to be an additive subgroup, it has to be of the form nz. Yeah, so we can use that fact. Yes, the proof is, I won't do that proof because we already saw that proof in subgroups. Uh, so I'll just write that. We know that any additive subgroup of Z is of the form in Z for n greater than or equal to 0, since every ideal of Z is an additive subgroup. Every ideal is necessarily of the form nz n greater than or equal to 0. Yeah, so every ideal has to be of this form. And we also saw that using the ring homomorphism um, that maps an integer to its equivalence class, every the kernel of that phi will be nz. So every nz is also an ideal. So we know every ideal of integers now. It is of the form nz for n greater than or equal to 0. Second, we don't need to check because we indirectly showed that using the we showed that the kernel is always an ideal. There we showed the second condition in general. When we showed that kernel of a ring homomorphism is an ideal of the ring of the domain ring, there we already showed that first and second property hold for every kernel of a ring homomorphism. So this is one particular example of a ring homomorphism, some Z to Z mod nz, whose kernel is nz. We'll do some problems now. Determine which of the following are rings. Is this a ring? Yes, yes. This is the ring of Gaussian integers. We have seen this in an example, I think. So if the coefficients a, b, and if you take another complex number c, d are integers, then whether you add the complex numbers or multiply them, the resulting coefficient will also be integers. So they will belong to this set. So they are closed. This has 1 in it, 0 in it. So they have identity in both addition and multiplication. Additive inverse is simply minus a minus ib for a plus ab. And minus a and minus b are also integers if a and b are integers. Associativity and distributivity simply follow because the operations are associative and distributive in the broader set of complex numbers. So they will be associative and distributive in this subset of complex numbers. This is a subset of C. So this is a ring that we already think seen. Or maybe we saw that it is a group. Now we know that it is a ring. Then what about instead of I, if I replace I by square root of 2, again A and B are integers. This is a subset of real numbers. Is this a ring? Square root 2 times B. 1 plus root 2. is a member. 1 plus 2 root 2 is a member. You can add a real number, or you can add a real number multiplied with square root 2. If it, let's see, AC plus AD root 2 plus BC root 2 plus root 2 BD. Can write this as AC plus 2 BD, which is an integer, plus AD plus BC into root 2. So AD plus BC is also an integer. So it is closed at least, and 1 belongs to it. You don't need to check associativity or distributivity. Commutativity is also fine. So it is a ring, right? So it is a ring. So you can replace I by square root 2 and it will still be a ring. You can replace square root 2 by other irrational numbers also. And same proof will hold. Okay, so this is a ring. We'll, this, the earlier ring, we actually denoted this by z of I in previous classes. The set of Gaussian integers. This is actually similar to saying it's a polynomial in I. But what would be a polynomial in I? A polynomial z of x is what? It's polynomials of the form ax square plus bx plus c, or ax cube plus bx square plus cx plus d. Whatever degree it is. It is of this form, right? Now if you replace this x by I, what would happen? What is ai square plus bi plus c? Yeah, it would be c minus a plus ib. So it would be of the form a plus ib for some a and b. Here also, if you had a I cube is simply minus I, and bi square is minus 1, ci plus d. This would also be of the form some p plus I into q. So all polynomials, if you take polynomials in I, then they are simply of the form a plus ib. So that's why the notation is also same. Write it as that of I. The same is true for here also. We can write this as z of square root 2. Because we have a x cube plus bx square plus cx plus d as z of x. You replace x by cube square root 2, you get square root 2 whole cube is 2 root 2. because root 2 cube is root 2 square into root 2. Root 2 square is 2. B into 2 plus C root 2 plus D. This will simply be 2B plus D plus 2A plus C into root 2. And these are both integers. So the powers of root 2 are simply 2 and root 2. So you don't get anything extra by taking powers of root 2. So this group is actually simply Z of root 2. Okay. Then next set is instead of taking an irrational like square root 2, what if I took a rational number a plus b by 2, a and b are in Z. This is a subset of rational numbers. Is this a ring? Yes, addition is no problem. Uh, no, you have to check it always. Uh, R plus is a subgroup. R plus is an abelian group. If you take a plus b by 2 and multiply with c plus d by 2, you get ac plus ad by 2 plus bc by 2 plus bd by 4. If bd by 4, you might not be able to eliminate that, right? Yeah. Some numbers bd by 4 might be of the form, might be just an integer, or it might be of the form some number by half. But it's not always the case. And so to prove that it is not always possible, you can give an example that should counter example should be enough. Simplest would be half. We saw that in one of the earlier lectures. Half is in R, but half into half is 1/4. It's not in R. This you can check yourself. Try to write a plus b by 2. Try to write 1/4 in as a plus b by 2. Then write b in terms of a or a in terms of b and see whether that can be an integer. That is, if you write 1/4 is a plus b by 2, then b is b by 2 is 1/4 minus a. So 1 minus 4a by 4. So b is 1 minus 4a divided by 2. But 1 minus 4a divided by 2 will not be an integer for any value of a. So it's not possible to write 1/4 as a plus b by 2. So this is not a ring. Then let R of x be a polynomial in x with coefficients in R, the real numbers. Let the ring R be set of all polynomials in set of all real polynomials whose degree is less than or equal to 3. Yes. Yeah, multiplication is not closed because, again, for negative statements, you can give a counter example. X square belongs to R, but x square into x square is x power 4, whose degree is 4. That does not belong to R. So multiplication is not closed. This is not a ring. What about so less than or equal to if I had greater than or equal to? There is no problem in multiplication, but there can be a problem in addition. Um, X power 4 belongs to R, and minus x power 4 plus x square belongs to R. Coefficients are real numbers, they can be negative also. No? If you add them, x power 4 plus minus 4 plus x square, it will be x square. That does not belong to R. So the degree may actually fall below. So this is also not a ring. Then let R be A by B, that is a rational number. 3 does not divide B. This is when written in the lowest terms. So actually, a rational number 1 by 2 is the same as rational number 2 by 4. It is the same as 3 by 6. So when we write 3 does not divide B, we mean when you already cancelled all the common factors, you return it in the lowest term, then 3 does not divide the denominator. Hmm. For this, we have to use one theorem or lemma we learned in the preliminaries or in the beginning stages. But if P is prime, then P divides AB means that P divides A or P divides B. Conversely, the contrapositive of that is that if P does not divide A and P does not divide B, then P does not divide AB whenever P is prime. So since 3 is prime, if 3 does not, let's say we have two numbers A by B and C by D, and 3 does not divide B and 3 does not divide D, then 3 won't divide BD. So this is a ring. But if the number we had taken here was not prime, for example, if we had rational numbers, that's that 4 does not divide. Now, this is no longer a ring. For example, half is in the ring because 4 does not divide 2. But half times half is 1 by 4. This is not in the ring. This is not in the set because 4 divides 2 into 2. So, yeah, we can write this in general that Rp, the set of all numbers of the form A by B, where P does not divide B. So instead of writing, P does not divide B, but here it's actually when A by B are in lowest terms. Now this is a ring. R Rn is a ring if and only if n is a prime number. A proof I won't write it. It's I think you understood it from the last two examples. Uh, there's no problem with we can show all the properties. Closure under addition, zero is an element because yeah, when it comes to zero, you can write zero as 0 by 1. That is the lowest term. Because any other number, 0 divided by 2, you can cancel out the 2 in both numerator and denominator because every number divides 0. When you write in lowest term, 0 is done as 0 by 1. So 0 by 1 is the identity. Then the addition obviously is defined as A by B plus C by D is AD plus BC by BD. So when you add A by B plus 0 by 1, you get A plus 0B by B, which is A by B. So 0 by 1 is the additive identity. Similarly, 1 can be written as 1 by 1. That is the multiplicative identity. Um, all other properties simply are inherited. Associativity and distributivity are simply inherited from those properties that addition and multiplication have in rational numbers. Then only closure with under multiplication is the doubtful part. And when n is a prime number, we use that prime number, that fact lemma, that if P divides AB, then P must divide A or P must divide B. So when this n is a prime number, closure holds, and when n is not prime, similar to the example we saw, where we had 4 does not divide B, then for 4 we took half. In general, for any n that is composite, what we mean by n is composite means that there exist two integers a and b, such that n is equal to a into b. Then 1 by a and 1 by b will be elements of R, and 1 by a into 1 by b is equal to 1 by ab, which is equal to 1 by n, which is not an element of R. I hope that is clear. If it's not clear, I'll write it down. Okay. The next set is set of numbers of the form a by 2 power n. So that a is an integer and n is a natural number. And by natural, I mean 0 is included in it. Is that what you consider as natural numbers? Okay. Then I'll write this as z plus. In some fields, natural numbers, computer science, in some courses, they consider 0 as part of natural numbers, and in some real analysis, actually, many courses they consider 0 as part of natural numbers, and in many courses they consider natural numbers to be from 1 and whole numbers will consider, so that includes 0. Okay. We'll call it Z. Even Z plus might be confusing. I'll just say N union 0. Okay. Now is this a ring? Suppose I have one number A by 2 power n, another number B by 2 power n, let's say. This would be A into 2 power n plus B into 2 power n by 2 power m plus n. If m and n are whole numbers, m plus n is also a whole number. And 2 power m and 2 power n are all whole numbers, so are all integers. So a into 2 power m plus b into 2 power n is also an integer. And suppose a into 2 power m plus b into 2 power n is also it also has factors of the form 2 power k, so that you cancel it from numerator and denominator. If you cancel 2 from 2 power m plus n, you will still be left with a number of the form 2 power n, 2 power something. So the denominator, even if there are common factors between the numerator and denominator, after adding, if you cancel some 2's from the denominator, it will still be of the form of power of 2. So addition is closed. Multiplication obviously AB by 2 power n plus n. Again, this is also closed. Additive identity 0, you can write it as 0 by 1, which is 0 by 2 power 0. 1 is 1 by 1, which is 1 by 2 power 0. They both belong to R. Rest of the properties are easy to verify. So it is a ring. Okay. Then let phi from R to R prime be a ring homomorphism. Kernel of phi is set of all elements in R such that phi of A is the zero element in R prime. What we have to do now is show that phi is injective. If and only if kernel of phi is the set containing 0, that is 0 R. Can I do this? No, injective is 1 to 1. So we have to show that, and by 1 to 1, mathematically we mean if phi of A is equal to phi of B, then A must be equal to B. That is only one element goes to image, one image. So if two elements have the same image, then they must have been the same element. Yeah, we have to show that if it is injective, if this property holds, then kernel of phi has only the zero element. Or that if kernel of phi has only the zero element, then it is injective. You can start with one direction first. I've written the definition. No? Yeah, set of all A in R such that phi of A is equal to 0 R prime. Here I have written. No, no, no. If it is injective, it's not. It means only one element of R maps to 0 R prime. 1 to 1 means for each element there is one image, and for each image there is only one pre-image. Only one element is mapped onto it. We have A, B, C, we have D, E, F. then only A maps onto D, B maps onto E, C maps onto F. Maybe there are other elements that are not mapped onto by anything. That is okay. Here you have 0 R prime, then you will have 0 R. We know that 0 R is mapped onto 0 R prime for every ring homomorphism. So that is the only element mapped onto 0 R prime. That's if the homomorphism is injective, then 0 R is the only element mapped onto 0 R prime. That's one direction. Yeah, first we have to assume one of the directions. Suppose kernel of P has only 0 R. We want to show that P is injective. To show that a function f is injective, we have to show that if f of x1 is equal to f of x2, then x1 is equal to x2. So assume let phi of a is equal to phi of b for some a and b. Then phi of a plus minus phi of b is equal to 0. You add minus phi of b on both sides. But minus phi of b, we saw that that is equal to phi of minus b. But phi is a homomorphism, so this is equal to phi of a minus b. What does this mean? This means a minus b belongs to kernel of p because phi of a minus b is 0 R. Right? But kernel of phi, we have assumed, suppose kernel of phi is 0 R only. That means a minus b is equal to 0 R, which means a is equal to b. So we have assumed that kernel of phi is 0 R and is a set containing 0 R. And we have shown that if phi of a is equal to phi of b, then a is equal to b. So we have shown that phi is injective. That's one direction. Next, suppose phi is injective. We want to show that kernel of phi has only one element. That we can do, we know that phi of 0 R is equal to 0 R prime. Suppose some other element belongs to kernel of phi. So since 0 R, phi of 0 R is 0 R prime, that means 0 R belongs to the kernel. Suppose some other element also belongs to, suppose some arbitrary element A belongs to the kernel. Then phi of A must be equal to 0 R prime. This means phi of A is equal to phi of 0 R. But since phi is injective, this means A is equal to 0 R. So 0 R is the only element in the kernel of phi if phi is injective. So we have proved both directions. Okay, all right. Next is let R be a ring. Show that R is a field if and only if the only ideals in R are the zero ideal and the ring itself. So let's first assume R is a field and let I be any ideal in R. We have to show that I is either the zero ideal or the entire ring. How will you do it? Yes, we are first we are showing one direction. We are assuming that R is a field. Then I let I be an ideal of R. We have to show that I has to be zero or R. How do you show that I is either zero or R? So if I is zero, we are done. Usually this type of question, this is how we proceed. You have to show something is one of two things. You say if it is the first thing, then okay. Then we assume that it is not the first thing. Then show it must be the second thing. So if I is equal to zero, we are done. We are saying it's either zero or R, right? I is zero, okay, we are good. Suppose I is not zero. Now you have to show that I is equal to R. Now how do you do that? Now since I is not equal to zero, there is some non-zero element in I, right? There exists A in I such that A is not equal to zero. R is a field, that's what you assumed. So A inverse belongs to R, right? It has a multiplicative inverse. Every non-zero element has a multiplicative inverse, and we are saying A is a non-zero element. Okay? What by no by pro, wait, by property? What is the property of an ideal? If some element is in the ideal, and for any other element in the ring, their product is in the ideal, right? A is in the ideal, A is not 0, so A inverse is in the ring. So their product must be in the ideal. Therefore, A inverse, which is 1, is in the ideal. Again, repeat that same argument. If some element is in the ideal and some element is in the ring, then their product must be in the ideal. 1 is in the ideal, R is in the ring. Suppose R is in the ring. Then 1 into R must be in the ideal. So I is equal to R. So that is one useful fact to remember. If 1 is in the ideal, then the ideal is simply the ring. Because the product of each ring element with 1 is the ring element itself. Product of each ring element with any element in the ideal must be in the ideal. So if 1 is in the ideal, the entire ring is in the ideal. So the ideal is simply the whole ring. So shown that either I has no non-zero elements, or if it has a non-zero element, since its inverse is also in the ring, because we are saying it is a field, then the product of the inverse and the element is in the ideal, which is 1. Since 1 is in the ideal is R. So we've shown one direction. If R is a field, then the only ideals possible are the zero ideal or the ring itself. Now we'll see the other direction. Suppose the only ideals of R are 0 and R itself. Now what do we do? I had told in another previous classes that we don't consider trivial rings. We don't consider zero ring. We always assume that there is at least one non-zero element. So let A be a non-zero element in the ring. Let A be any non-zero element. Pick any non-zero element. Then consider this set I is defined to be R times A for all R in R. You simply multiply every element in the ring by A and take that set. Since in a group, what will happen if you simply add one of the group elements to all the elements in the group, you'll get back the group. That is because if you add A to B and C, A plus B is equal to A plus C, then since there A has a additive inverse, so in a group what happened, A plus B, if you said A plus B is equal to A plus C for two different group elements, if B is not equal to C. Sorry, if B and C were two elements, you don't know whether B is equal to C or B is not equal to B, and you added A to both of them and you got A plus B is equal to A plus C. Then you could add minus A to both sides. Then you would get B is equal to C. So that means if you add A to two different, the contrapositive of this is that if B is not equal to C, A plus B is not equal to A plus C. That means if you have two different group elements and you add the same element to it, you again end up with two different group elements. So in if you pick the group element and added it to every other or every element in the group, you would in the end get back the group, right? Is that clear? You remember the Cayley table? You had element B, C, D, A, B, C, D. Then you had A, B, C, D. This element was at A plus A, right? This element was A plus B. This was A plus C. This was A plus B. Correct, right? Remember that? Then we saw a property that every element occurs at least once in the row. Every element of the group occurs exactly once in the row, right? And every element of the group occurs exactly once in the column. So what does that actually mean? That means you're adding A to every element of A of the group A, B, C, D, huh? And you're getting the group back, right? No. If every element of the group occurs once in each row, that row is the group itself, right? Uh, It's just some rearranged version of the group, that's all. So if you add some element of the group to every other element of the group, you will get back the group itself. That is because of the existence of additive inverse. That ensures that when you add A to two different elements, B and C, you will get two different group elements. A plus B and A plus C are different. Similarly, A plus B, A plus C, A plus D are all different. That is A plus every element of the group, you get a distinct element each time. And since due to closure, they are all in the group. So you have, if this had n elements here, if the group had n elements, when you added A to each of the n elements, you got a different set of n elements. But due to closure, they're also all group elements itself. So the only possibility is that you got back the group. For example, if you had Z4, 0, 1, 2, 3, you added 2 to each element. 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 is 4, but modulo 4 it is 0. 2 plus 3 is 5, but modulo 4 it is 1. So you get 2, 3, 0. It's rearranged, that's all. But the elements are the same. Now, for a ring that does not need to that does not happen. I mean, it's not a necessity that if you multiply like this, what I've written the set I, if you multiply each element in the ring by A, all of them might not be distinct elements. You might get a smaller set and the ring itself. But this is an ideal, at least. That is true. You can verify. I'll leave it that to you. Verify that this is an ideal. It is called the ideal generated by A. So in groups we had in under multiplicative group the subgroup generated by A was A square, A cube, A power minus 1, A power 0, all the powers of A. And in terms of additive group it was A, 2A, 3A, 0 times A, minus 1 times A. That was the subgroup generated by A. Here the ideal generated by A is this. You take A and multiply with each element in the ring R. Okay, this once you verify that it is an ideal, now what? There are only two possibilities, right? Our assumption was what? Suppose that the only ideals of R are 0 and R itself. So this I must either be the 0 ideal or it must be R itself, right? Yes, A is not equal to 0. By hypothesis, I equal to 0 or I equal to R, but A is not equal to 0 and A belongs to I. Therefore, I is equal to R. What does that mean? I is equal to R means 1 belongs to I. 1 belongs to I. So for some R, but all the elements of I are of the form R times A, right? So for some R times A is equal to 1, which implies R equals A inverse. This is A as an inverse. This is true for any non-zero A in R. If you consider the ideal generated by 0, it is the 0 ideal. If you consider the ideal generated by any non-zero element in the ring, then it is the ring itself. And since it's the ring itself, one should belong to that ideal. Since one belongs to that ideal, all the members of the ideal are of the form R times A. So one should also be of the form R times A for some R. For each A, there will be a different R. So what does that mean? Yeah. So therefore, R is a field. So we have shown both sides. So in any ring, if the ring is actually a field also, that is possible if and only if the only ideals in it are 0 and R. So if you actually had a ring homomorphism, if you had a ring homomorphism from a field to a ring, what would happen then? The kernel of the ring homomorphism is a ideal of the domain. The domain is a field now. So the kernel would either be zero ideal or the entire field itself. But it can't be the entire field because by definition of the homomorphism or ring homomorphism, P of 1 must be 1. So 1 can never be in the kernel. Kernel is set of all elements that are mapped to 0. Right? So the kernel cannot be the entire field. So the kernel has to be the zero ideal. And we saw in the previous example is the kernel is the zero ideal, then P must be injective. So if we had a ring homomorphism from a field to a ring, then it must be injective. So that is one way in which you can use this theorem. So when you are trying to classify the types of homomorphisms that might exist between fields and rings, you already know for sure that you only have injective homomorphisms from a field to a ring. Okay, we'll stop. That's it for today. I'll see you tomorrow.